And we are live. What is up, everyone? This is Tyler. Welcome back to another video, or if you're watching this live as it happens, welcome to the Hack Smarter Twist channel. Good to have you hanging out with me tonight, and we are going to dive into some more Rust programming. So if you missed day one, you can catch it on my YouTube page, but in day one, we just dug into the official Rust documentation. They have a really good, essentially ebook online on their website that guides you through programming in Rust. And day one, we spent about 2 hours. We got Rust set up. We got kind of the basics understood in the language and using cargo to build some projects. And we made our first game, a guessing a random number game. Have not looked at Rust since that day. I was sick one day, and then yesterday I streamed some Try Hack Me stuff. But today, we are back in learning the Rust programming language. And if this is one of your first times watching either on Twitch or maybe on YouTube, let me give you kind of a glimpse of what to expect. I do not know how to program in Rust. All right, so if you're looking for an expert to teach you how to program, go to YouTube and find a different person who knows what they're talking about. I'm learning this as we go. So what we're doing is we're working through the documentation together, we're programming together, we're making mistakes together, and hopefully by the end we learn something through this process. At least I know I'm going to learn something. Hopefully you learn something through this process as well. So I would encourage you to follow along as we do this. Let me go ahead and share my screen, which I don't know if I am sharing the right screen. Let's check. Nope, I'm not sharing the right screen. Let me fix my brokenness real quick. And there we go. Now we're sharing the right screen, so you guys aren't seeing OBS like freaking out when I switch over. But I have the documentation open here. You can get to this just by docrustlang.org. And actually, before we dive into this, we should probably just review what we did last time, honestly, for my own benefit, so I can remember exactly what we did. So if we go over to our programming folder, CD Rust. All right, what do we have here? We have Rust Scan, that's right. We downloaded Rust Scan for fun. We have our guessing game there. So if we CD to our guessing game, and if we, was it cargo run? That's how you do it, if I remember. What? Do I still need a, I thought I added it to my path variable. Hold up 1 second. I don't know if I accidentally screwed something up. I don't think we have to reinstall Rust. I thought I added it to my path. Maybe I just did it for that shell. Blah, blah, blah. And I assumed it would do it right away when we installed the program. I'm just glancing through some stuff on my other screen. I'll have to rewatch my own video to remember how I did this. We installed Rust. You can add the following. Okay, let's maybe we didn't add this to our actual bash profile. So if we do, is it Pluma? Is that what it is in Parrot? Yeah, Pluma. So if we do sudo Pluma, and if we try something like this, I don't know if I actually did that right. Well, we can try. No. Okay, so I'm just going to do it manually, and I'll mess with this later. I think it's source, home, cargo, environment like that. Okay, so now we at least have it in this terminal. But let's go ahead and do another terminal and add it there as well. And I'll figure out why the heck it's not working in my actual path variable when I installed it, but we'll figure that out later. Okay. Now that we got that done, now we can try to do cargo run on our guessing game. I think it's cargo run. There we go. So let's guess our number. If we start with 50, it says too small. Let's go to 60, too small, 70, too small, 80. Too big, so how about 75? Too small, so 76, 77, and we won. So that's our game. Let's see if we can remember what the source code actually looks like for our game. And let me get Twitch pulled up on the side so I can watch the chat over there. If anyone's watching on Twitch and you have a Twitch account, just let me know if the audio and everything sounds good to you guys. I would appreciate that. So if we Pluma main rs let's just read through this code to remind ourselves of how this works. So in the beginning, we're importing our libraries. std is our standard library. We have io, which is input-output library. We have this comparison library. And then we have this random library. That's how we are generating our random number. We have fn main. So this is what everything is inside, is this main function right here. We're printing a line called guess the number. Then we're setting a variable called secret number, let secret number equal, and then we're pulling from the random library up there, and we're saying give us a random number between the numbers of 1 and 100. So it's setting our random number. I commented out this line. This is when we were first setting it up, just so we knew what the secret number was. Once you're done, you can comment that out. And then we set up a loop. If you can see this, we printed a line. This continues to loop until the person playing the game gets the number correct. So it says, please input your guess. And then we are defining a new variable called guess, and we're using this mute, which means make the guess variable mutable. By default, variables in Rust are not mutable. If you remember that, they don't change. So we have to specify, make this guess variable mutable. String new. So it's of course a string. And then it's a new variable, I believe is how we're understanding this new kind of function. We have our input output. This is how we're getting input from the user. So we're reading the guess variable from the user as we're asking the user, please input your guess. If they input something like Tyler, it'll say fail to reline because it's not a number. Let's see, let guess U32. This is specifying the type of integer, if I recall. Match guess trim parse. So now we're taking the number and we have to trim it. When we first get the number in the Rust program, I believe Rust takes it as a string. What we're doing here is we're converting it from a string to a U32 integer, so then we can compare it. If you don't do that, you get a type error, if my memory serves me correct. And this is kind of like a catch statement. If it's a number, we can continue. If it's not, or if it's, let's see, okay number. Remember, there's okay and error. So if it's okay, if it's a number, we continue to go on. If it's not, I think we redo the loop again, because then it says, hey, you didn't give us a number, so we're going to ask you to input your guess again. You guess that. Of course, it's going to show us what our guess is. And then here is where we're pulling in this comparison library. If your guess is okay, I'm totally stumbling my way through that, but that's okay. We're matching, right? So this is comparison. Here's our guess from up there, so what the user guesses, and we're comparing it to the secret number variable that we set up here. So we're comparing these two. We're comparing guess to secret number. And then if it's a less than, it's going to print too small. If it's greater, if the secret number is greater, it's going to say too big. And if it's equal, it says you win. And then we break out of our loop and the game is over. So that's just a reminder of some of the code and some of the syntax that we learn about in day 1 of our Rust programming series. What I think I'm going to do is doing 2 chapters all at once is almost too much. Talking for 2 hours straight was a lot of talking. So my goal is to take this chapter by chapter. And so today we're going to do our best to make our way through chapter 3. And I think the way I want to do that is if I put this on one side of my screen, and if we pull up my terminal, and let's just put this on this side of the screen, we can close that main right there. And now we can kind of program as we do these things. We'll see kind of what project we're going to make, what it tells us to make, but for now we can clear. All right, let's dive in. If you're following along, I encourage you, get your terminal out. If Rust is not in your path variable either, troubleshoot that on your own. That's what I'm going to do. I don't know why it didn't work at first. Common programming concepts. This chapter covers concepts that appear in almost every programming language and how they work in Rust. Many programming languages have much in common at their core. None of the concepts presented in this chapter are unique to Rust, but we'll discuss them in the context of Rust and explain the conventions around using these concepts. Specifically, you'll learn about variables, basic types, functions, comments, and control flow. These foundations will be in every Rust program, and learning them early will give you a strong core to start from. Sounds good. I should glance over to the chat. I know those of you on YouTube can't see the Twitch chat, just a plug. You should watch me live on Twitch. We can interact, we can chat, we can hang out together. Want to say hi to S-Brand. He's often on the stream. Hi, S-Brand, and Tyler Ramsbey fan. The best username I've seen. Good to have you here as well. All right, keywords. The Rust language has a set of keywords that are reserved for use by the language only, much as in other languages. Keep in mind that you cannot use these words as names of variables or functions. Most of the keywords have special meanings, and you'll be using them to do various tasks in your Rust programs. A few have no current functionality associated with them, but have been reserved for functionality that might be added to Rust in the future. You can find a list of the keywords in Appendix A. That's pretty common. Variables and mutability. As mentioned in storing values with variables section, by default, variables are immutable, and that's what I shared about before. This is one of the many nudges Rust gives you to write your code in a way that takes advantage of the safety and easy concurrency that Rust offers. However, you still have the option to make your variables immutable. Let's explore how and why Rust encourages you to favor immutability and why sometimes you might want to opt out. When a variable is immutable, once a value is bound to a name, you cannot change that value. To illustrate this, generate a new project called variables in your projects directory by using cargo new variable. So let's do that. Cargo new variables. Okay, let's cd to variables and then cd to source. And there is that, pluma main.rs. Let's get pluma open. Put it over here. Okay, then in your new variables directory, open main.rs, and we did, and replace its code with the following code, which won't compile just yet. And I understand that we can totally copy and paste this, but I like to just type the code because it helps build that muscle memory as you're learning how to code. Type it all out and even make mistakes as you go. So we're going to set a variable called x. And by default, it's going to be immutable, which means it doesn't change. So let x equal 5. Jump down here, and then print. It almost looks like the tabs are off. Maybe they're not. Maybe it's just my eyes playing a trick on me. Print line. The value of x is, and then we're pulling that variable in like that. And then x equals 6, which you cannot do, right? We can't change the variable. It is immutable. So either we're going to get an error or it's going to remain 5, I would assume. So print line. The value of x is x like that. And there we go. Save and run the program using cargo run. All right, let's save and we'll open up our terminal. We'll actually go to this one, cd out, and then what was this, variables like that, cargo run. It's going to build it, and here's our error. Cannot assign twice to immutable variable x, which I called that when we were doing it. Let x equals 5's first assignment to x. Help. Consider making this binding mutable by adding mute x. Cannot assign to twice immutable variable. Yep. Okay, you should receive the error message, which we did. This example shows how the compiler helps you find errors in your programs. Compiler errors can be frustrating, but really they only mean your program isn't safely doing what you wanted to do yet. They do not mean that you're not a good programmer. Experienced Rusticians still get compiler errors. Or you're like me and you can't even add it to your path variable properly. You receive the error message, cannot assign twice to immutable variable x because you tried to assign a second value to the immutable x variable. It's important that we get compile time errors when we attempt to change a value that's designated as immutable because this very situation can lead to bugs. If one part of our code operates on the assumption that a value will never change and another part of our code changes that value, it's possible that the first part of the code won't do what it was designed to do. The cause of this kind of bug can be difficult to track down after the fact, especially when the second piece of code changes the value only sometimes. The Rust compiler guarantees that when you state that a value won't change, it really won't change. So you don't have to keep track of it yourself. Your code is thus easier to reason through. But mutability can be very useful and can make code more convenient to write. Although variables are immutable by default, you can make them mutable by adding mute in front of the variable name as we did in Chapter 2. Adding mute also conveys intent to future readers of the code by indicating that other parts of the code will be changing this variable's value. For example, let's change this to the following. So we're going to add mute here, let mute x equal 5, and they're going to change x to 6, and then let's save that, and let's go ahead and try to run it. Okay, and it printed out properly. The value of x is 5, and the value of x is 6. It successfully updated that variable. We were allowed to change the value bound to x from 5 to 6 when mut is used. Ultimately, deciding whether to use mutability or not is up to us and depends on what you think is clearest in that particular situation. Constants. Like immutable variables, constants are values that are bound to a name and are not allowed to change, but there are a few differences between constants and variables. First, you aren't allowed to use mut with constants. Constants aren't just immutable by default, they're always immutable. You declare constants using the const keyword instead of the let keyword, and the type of the value must be annotated. We'll cover types and type annotations in the next section, data types, so don't worry about the details right now, just know that you must always annotate the type. Got it. Constants can be declared in any scope, including the global scope, which makes them useful for values that many parts of code need to know about. The last difference is that constants may be set only to a constant expression, not the result of a value that could only be computed at runtime. Here's an example of a constant declaration. All right, so let's go ahead and declare this constant declaration in our own code for practice. So const, we're declaring it, and then 3 hours in seconds, that's a variable name. And I notice a few things. Our U32, this is where we're declaring the type, right? This is an integer. So U32, we're declaring the type, kind of like it says, and then 60 times 60 times 3, and then we're closing it out. The constant's name is 3 hours in seconds, and its value is set to the result of multiplying 60, the number of seconds in a minute, by 60, the number of minutes in an hour, by 3, the number of hours we want to count in this program. Rust's naming convention for constants is to use all uppercases with underscores between words. The compiler is able to evaluate a limited set of operations at compile time, which lets us choose to write out this value in a way that's easier to understand and verify, rather than setting this constant to the value of 10,800. See the Rust reference section on constant evaluation for more information on what operations can be used when declaring constants. Constants are valid for the entire time a program runs, right? They're constant within the scope in which they were declared. This property makes constants useful for values in your application domain that multiple parts of the program might need to know about, such as the maximum number of points any player of a game is allowed to earn or the speed of light. Naming hard-coded values used throughout your program as constants is useful in conveying the meaning of that value to future maintainers of the code. It also helps to have only one place in your code you would need to change if the hard-coded value needed to be updated in the future. Shadowing. As you saw in the guessing game tutorial in chapter 2, you can declare a new variable with the same name as a previous variable. Rusticians say that the first variable is shadowed by the second, which means that the second variable is what the compiler will see when you use the name of the variable. Got it. In effect, the second variable overshadows the first, taking any uses of the variable name to itself until either it itself is shadowed or the scope ends. We can shadow a variable by using the same variable's name and repeating the use of the let keyword as follows. Okay, let's go ahead and just type this code out. Once again, just for our own practice, let x equal 5, let x equals x plus 1. And then it looks like we are doing that. And then remember, it's 4 spaces, 1, 2, 3, 4. Let x equals x times 2. So we are, if you see this, we have x equals 5. And then let x equals 5 plus 1. So that means let it equal 6. And then let x equal 6 times 2. So now x would be 12. I'm curious if this will work because these are technically immutable, but if we're allowed to overshadow, then it should work, right? Print line, the value of x in the inner scope is x, like that. And then 1, 2, 3, 4. Oh, maybe I went back too far. Nope, one more. Like that, we'll close that out. And then print line, the value of x is x, like that. Okay, interesting. Let's go ahead and run it ourselves and see if we can walk our way through this. Cargo run. Okay, we have an error. Oh, add this here. Oh, duh. Thank you. Thank you for the helpful thing. Make sure you close your lines with that. Let's save it, and let's try to cargo run that beast again. There we go. The value of x in the inner scope is 12. The value of x is 6. Okay. So why is it like that? Well, we have x equals 5 here, and then x equals x plus 1. So right now x is 6. Now we have this inner scope right here. So this is different than this outer scope. And in our inner scope, we have x equals 6 times 2. Therefore, x is going to be 12. So the inner scope is 12, but it did not update it in the outer scope. So the outer scope is still what x is defined here, which is 6. Okay? That makes sense in my own head. Hopefully it makes sense for you. I understand what they are doing there. The program first binds x to a value of 5, then it creates a new variable x by repeating let x equals, taking the original value and adding 1 so the value of x is then 6. Then, within an inner scope created with the curly brackets, the third let statement also shadows x and creates a new variable, multiplying the previous value by 2 to give x a value of 12. When that scope is over, the inner shadowing ends and x returns to being 6. When we run this program, it will output the following. Yep, it worked for us. Shadowing is different from marking a variable as mutable because we'll get a compile time error if we accidentally try to reassign to this variable without using the let keyword. So if you remember, if we did like let x equals 5 and then we did x equals 6 without defining almost like a new variable, that's how we got that error. That's why it worked that time. That makes sense. The difference, let's see, where was that? By using let, we can perform a few transformations on a value, but have the variable be immutable after those transformations have been completed. The other difference between mute and shadowing is that because we're effectively creating a new variable when we use a let keyword again, we can change the type of the value, but reuse the same name. For example, say our program asks a user to show how many spaces they want between some text by inputting space characters, and then we want to store that input as a number. Okay, let's go ahead and do that as well. Let's follow along with all these examples. So let spaces equal, and we'll just do 4 spaces, 1, 2, 3, 4, like that. Let spaces equal spaces. Ooh, that looks a lot like Python. Length, like that. The first spaces variable is a string type, and the second spaces variable is a number type. Shadowing thus spares us from having to come up with different names such as spaces string and spaces num. Instead, we can reuse a simpler spaces name. However, if we try to use mute for this as shown here, we'll get a compile time error. So if we use mute, let mutable spaces, so in other words, let spaces be able to be updated. The problem with this is we're defining spaces as being a string, but when we do it down here, we're changing it to an integer. So the only way for that to work is essentially we have to create a new variable called spaces. We can't just change the same spaces variable by making it mutable. I'm pretty sure that's why it fails. Let's go ahead and run it and see if I am correct. Yeah, so help. If this is intentional, prefix it with an underscore, spaces. I see unused variable spaces. Note, unused variable on by default. Variable does not need to be mutable. Help, remove this mutable on by default. Okay. And we're getting the same error, I think. Well, our error is slightly different. It might just be more updated because it's telling us, hey, you don't actually need this, but in their error it says mismatched types, which is what I was expecting because we have a string and then we have an integer type. But let's go ahead and keep going. Oh, is that the end of chapter 3? Oh, no, okay. Chapter 3 has quite a few parts. Data types. Every value in Rust is of a certain data type. Let's get this pulled back up, which tells Rust what kind of data is being specified so it knows how to work with that data. We'll look at 2 data type subsets, scalar, I'm going to call it scalar, and compound. Keep in mind that Rust is a statically? Do they mean statically? Oh, statically. Rust is a statically typed language. I'm thinking statistically. Statically typed language, which means that it must know the types of all variables at compile time. The compiler can usually infer what type we want to use based on the value and how we use it. In cases when many types are possible, such as when we converted a string to a numeric type using parse in the comparing the guess to the secret number section in chapter 2, we must add a type annotation like this. And once again, let's type it out ourselves, build that coding muscle memory. So let guess, this is from that. And remember, we updated the type, the integer type, to U32 equal 42 parse expect not a number. So if it doesn't parse, it's saying it's not a number. If we don't add the U32 type annotation shown in the preceding code, Rust will display the following error, which means the compiler needs more information from us to know which type we want to use. So let's go ahead and, I guess we don't need to break it. We can see it here. Consider giving guess a type. And here we're giving guess a type, therefore it works. You'll see different type of annotations for other data types. Scalar types. A scalar type represents a single value. Rust has 4 primary scalar types: integers, floating point numbers, booleans, and characters. You may recognize these from other programming languages. Let's jump into how they work in Rust. Integer. An integer is a number without a fractional component. We use one integer type in chapter 2, the U32 type. This type declaration indicates the value it's associated with should be an unsigned integer. Signed integer types start with I instead of U. Okay, signed is I, unsigned is U. That takes up 32 bits of space. Table 3-1 shows the built-in integer types in Rust. We can use any of these variants to declare the type of an integer value. Okay, so 8-bit, I8, unsigned. Okay, that all makes sense. I'm going to get a drink of water. Each variant can be either signed or unsigned and has an explicit size. Signed and unsigned refer to what is possible for the number to be, or whether it's possible for the number to be negative. In other words, whether the number needs to have a sign with it, sign, or whether it will only ever be positive. It can therefore be represented without a sign, unsigned. So -1 is signed, 1 is unsigned. It's like writing numbers on paper. When the sign matters, a number is shown with a plus sign or a minus sign. I was thinking of like signing a signature. So it's just like a sign in that way. However, when it's safe to assume the number is positive, it's shown with no sign. Signed numbers are stored using 2's complement representation. The heck is that? To reversibly convert a positive binary number into a negative binary number. Okay, I'm having PTSD from math class, but I think I vaguely remember that. Each sign variant can store numbers from -2 to the n power -1 to 2 to the n power -1 inclusive, obviously, where n is the number of bits that variant uses. So an I8 can store numbers from 27 to 27 -1, which equals 128 to 127. Unsigned variants can store numbers from 0 to 2n -1, so a U8 can store numbers from 0 to 28 -1, which equals 0 to 255. Okay, so it's binary. I get that because I'm thinking of IP addresses when we see that. Additionally, the I size and U size types depend on the architecture of your computer your program is running on, which is denoted in the table as Arch. 64 bits if you're on a 64-bit architecture and 32 bits if you're on a 32-bit architecture. You can write integer literals in any of the forms shown in table 3-2. Note that number literals that can be multiple numeric types allow a type suffix, such as 57U8, to designate the type. Number literals can also use an underscore as a visual separator to make the number easier to read, such as 1000, which are the same values if you had specified 1000. Okay, got it. So decimal, here's our example. It would be 98.222, I think, or 98,222. Hex, of course, octal, binary, and byte. So, how do you know which type of integer to use? If you're unsure, Rust's defaults are generally good places to start. Integer types default to I32. Which means it's signed, which means it can be a negative or a positive. The primary situation in which you'd use I size or U size is when indexing some sort of collection. Integer overflow. Let's say you have a variable type of U8, so that's kind of our byte right there that can hold values between 0 and 255. If you try to change a variable to a value outside of that range, such as 256, integer overflow will occur, which can result in one of two behaviors. When you're compiling in debug mode, Rust includes checks for integer overflow that cause your program to panic at runtime if this behavior occurs. Hope you guys like that. Rust uses the term panicking when a program exits with an error. We'll discuss panics in more depth. I'm sick of doing that. In the unrecoverable errors with panic section in Chapter 9. When you're compiling in release mode with the release flag, Rust does not include checks for integer overflow that cause panics. Instead, if overflow occurs, Rust performs twos complement wrapping. In short, values greater than the maximum value the type can hold wrap around to the minimum of the values the type can hold. In the case of U8, the value 256 becomes 0, the value 257 becomes 1, and so on. That makes sense. The program won't panic, but the variable will have a value that probably isn't what you were expecting it to have. Relying on integer overflows wrapping behavior is considered an error. Don't do it. To explicitly handle the possibility of overflow, you can use these families of methods provided by the standard library for primitive numeric types. Wrap in all modes with the wrapping methods. All right, we got to become wrappers, such as wrapping add. Return the none value if there is an overflow with the checked methods. Return the value and a boolean indicating whether there was an overflow with the overflowing methods, and saturate at the value's minimum or maximum values with the saturating methods. Got it. Floating points. Let's float around. Rust also has two primitive types for floating point numbers, which are numbers with decimal points. Rust floating point types are F32 and F64, F for float, which are 32-bit and 64 bits in size, respectively. The default type is F64 because on modern CPUs it's roughly the same speed as F32, but is capable of more precision. All floating point types are signed, which means they can be negative or positive. Here's an example that shows floating point numbers in action. All right, let's go ahead and see these floating point numbers in action. Doesn't just sound exciting. Let x equals 2.0, right? That's F64. And let y, we're defining the type now. A type of floating 32 equals 3.0, and that's F32. Floating point numbers are represented according to IEEE 754 standard. The F32 type is a single precision float, and F64 has double precision. Numeric operations. Rust supports the basic mathematical operations you'd expect for all the number types: addition, subtraction, multiplication, division, and remainder. Integer division truncates toward 0 to the nearest integer. The following code shows how to use numeric operation in a let statement. All right. Well, once again, let's build that muscle memory. Addition is let sum equals 5 plus 10. So we're defining sum. That makes sense. Let's do subtraction. Well, it's just subtraction. There we go. Let difference equals 95.5 minus 4.3. Of course, that's going to be floating points there. Multiplication. If I can type, let product equals 4 times 30. And division, let quotient equal 56.7 divided by 32.2, like that. And let truncated equal -5 divided by 3, which says it results in -1. Okay. And finally, good old remainder. Let remainder equal 43 opulus thingy, whatever that thing is called, or percent sign, like that. Each expression in these statements uses a mathematical operator and evaluates to a single value, which is then bound to a variable. Appendix B contains a list of all operators that Rust provides. Okay. And then I suppose we could just print line each one of these if we wanted to, and maybe we can, just for practice. It would be print line like that. I'll print line like that. And then could we just print like the sum is sum? Would that work? I'm curious. Let's just try to run that. Cargo run. Shoot. If this is intentional, prefix it. Unused variable remainder. If this is oh. I mean, I copied it from there. Let's see if we can understand this error. Help. If this is intentional, prefix it with an underscore. Difference. This is intentional, prefix it with an underscore. Unused variable difference. Oh, it's just because I didn't actually do anything with those. It says prefix them with an underscore. So if we don't use them, can we just prefix them with an underscore? Is that what it's saying? Look, we're learning something on our own. Wonder what this does. Does that do anything? Let's try that. Ah, it worked. The sum is 15, and if you prefix the other ones with an underscore, that tells Rust, hey, I wanted to find these variables, but in the program right now, I don't need them, so you can ignore them. If you don't do that, it gets mad and says, hey, these are variables that aren't being used. We learned something with our own experiments. The Boolean type. Okay, we can erase all this stuff it looks like. Let's talk about Booleans. As in most other programming languages, a Boolean type in Rust has two possible values, true and false. Booleans are 1 byte in size. The Boolean type in Rust is specified using bool. For example, let t equal true, all right, and let f, we're defining the type, we're defining it as bool, equals false, with explicit type annotation. The main way to use Boolean values is through conditionals, such as an if expression. We'll cover how if expressions work in Rust in the control flow section. I do not existist. I like your name. It worked in the previous run too. Those are just warnings. Oh, thank you for telling me. I didn't even catch that. Good call. Hey, I do not existist. Have you programmed in Rust before? Like, do you know Rust programming? Would love for you to call me out if I'm doing stuff that's silly, because that's a good way to learn. Okay, the character type. Looks like we're not doing much with that. The character type. Rust character type is the language's most primitive alphabet type. Here are some examples of declaring character values. So let's declare some character values. We have f in main, so let c equal z. That doesn't make any sense. Let z character, so we're defining the type, z like that. And of course with explicit type annotation. And I do not exist. This said, no, I'm learning with you now. Okay, you must have just saw that it actually worked. Good catch, though. Let heart-eyed cat equal. Oh, what a pretty little kitty. Can I just copy it like that? Okay, mine looks a little bit different. It works, though. Let heart-eyed cat equal that thing. Can we actually print that? Let's do a print line like that, exclamation mark, and C is apparently C, whereas Z is Z like that, and the cat is heart-eyed cat. You guys think that'll print properly? I don't know. Let's find out. Oh, I think I need that at the end there. Okay, let's see if that prints. C is apparently C, whereas Z is Z, and the cat is heart-eyed cat. Cannot find value Z in the scope. Compiling variables. Help. A local variable with a similar name exists. Notice the capitalization. Is that because we are defining, it says one with a similar expression already exists. Is that because we're calling that Z? So if we just change this to C, because, you know, that makes a lot more sense, then does it compile? Nope. Variable with a similar name exists. Notice the capitalization, Z. Okay. What if I delete these? I just want to see my cat. I want to see if that actually prints out. What? Oh, okay, gotcha. Let's go like this. And the cat is. That works for me. Simple. Oh, it made it. Okay, cool. I do not exist. It says Z needs to be Z, I think. Oh, I see what you're saying. You're right. They didn't actually do a real Z. They like made a weird character Z. Good call. Good call. That's why it wasn't working there. Okay, note that we specify care literally with single quotes. Let's pull this back up, although I deleted my stuff, as opposed to string literals, which use double quotes. I did not notice that. Rust character type is 4 bytes in size and represents a Unicode scalar value, which means it can represent a lot more than just ASCII. Accented letters, Chinese, Japanese, and Korean characters, emoji, and zero with spaces are all valid character values in Rust. Unicode scalar values range from you, that, to that, to that, and to that. Inclusive, of course. However, a character isn't really a concept in Unicode, so your human intuition for what a character is may not match up with what a character is in Rust. We'll discuss this topic in detail in Store and UTF-8 encoded text with strings in Chapter 8. Compound types. Compound types can group multiple values into one type. Rust has 2 primitive compound types, tuples and arrays, like many other programming languages. Tuple. The tuple is a general way of grouping together a number of values with a variety of types into one compound type. Tuples have a fixed length. Once declared, they cannot grow or shrink in size. We create a tuple by writing a comma-separated list of values inside parentheses. Each position in the tuple has a type, and the types of the different values in the tuple don't have to be the same. We've added optional type annotations in this example. All right, let's go ahead and try this example ourselves. So let tup, and we're specifying the type. So the first one is sign 32, the second one is architecture 64, and the third is the U8 character, and it just has to correspond, right? So 500, 6.4, 1, like that. And if we do print line like that, and can we just call tup in that way? Would that work? I don't know. Nope, cannot compile variables due to previous error. You might be missing a string literal to format with. Okay, so if we do, how about like that? I think that's all we need. Try that. Oh, wrong terminal. Okay, tup i32f64u8 cannot be formatted with the default formatter. Help, the trait things is not implemented. In format strings, you may be able to use that question mark. This error originates in the macro create format args, which comes from the expression of the macro print line. For more information, well, that's how they're doing it. Let's keep reading. We're probably just missing something. I'm working ahead, but sometimes that's a good way to learn. So we did that. Let's delete this line. Just this line. And everything else looks the same as them, right? Let tup equal those things. Okay. The variable tup binds to the entire tuple because a tuple is considered a single compound element. To get the individual values out of a tuple, we can use pattern matching to destructure a tuple value like this. Okay. So maybe that's what we had to do before printing it. So we're destructuring it. Let x, y, and z equals the tuple. So then x would be 500, y would be 6.4, and z would be 1, I'd assume. And let's print line like that. The value of y is like that. What do you guys think y would be? My guess is either it's going to error because I did something wrong. That's my first guess. My second guess is it will be 6.4 is what it should be. Let's see which guess is right. Okay, so it actually came out down here, kind of like what I do not existist over in the Twitch chat is saying. These are errors. So it's not necessarily saying this is wrong because they're saying we have an unused variable x and unused variable z because we didn't use x and z. We only wanted to see what y was. So not errors, more of warnings. It did correctly say that y is 6.4, so the program worked correctly. The program first creates a tuple and binds it to the variable tup, and then uses a pattern with let to take tup and turn it into 3 separate variables, x, y, and z. This is called destructuring because it breaks the single tuple into 3 parts. Finally, the program prints the value of y, which is 6.4. We can also access a tuple element directly by using a period followed by the index of the value we want to access. For example, okay, I think we're keeping our tuple the same. Let 500 equal x dot 0. So that makes sense. It's almost like a list in Python. We're pulling it from, or a tuple. X dot 0 referring to 0 right here. This would be 1, and this would be 2. Right? So let 6.4 equal x.1. And if that confuses you, if you're new to programming, computers start counting at 0, not 1. So this is 0, 1, 2 is how programming and computers count in general. And let 1 equals x.2 like that. And then we're defining each one of those. This program creates the tuple x, which is right there, and then accesses each element of the tuple using their respective indices, which we actually didn't do that. We need to change tuple to x. If we had tuple, we would just change these to tup and it would work as well, but we need to change that to x so it's defining them properly. As with most programming languages, the first index in a tuple is 0, and that's what I said. The tuple without any values has a special name, a unit. This value and its corresponding type are both written as parentheses and represent an empty value or an empty return type. Expressions implicitly return the unit value if they don't return any other value. Got it. A drink of water. Lots of talking. Already an hour. I don't know if we'll make it through all of chapter 3 or not. The array type. Another way to have a collection of multiple values is with an array. Unlike a tuple, every element of an array must have the same type. Unlike arrays in some other languages, arrays in Rust have a fixed length. We write the values in an array as a comma-separated list inside of square brackets. Okay, let's go ahead and make our array here. Let A equal, and then square brackets, 1, 2, 3, 4, 5. Close our square bracket and do our semicolon. Arrays are useful when you want your data allocated on the stack rather than the heap. That reminds me of buffer overflows. We will discuss the stack and the heap more in chapter 4, or when you want to ensure you always have a fixed number of elements. An array isn't as flexible as the vector type, though. A vector is a similar collection type provided by the standard library that is allowed to grow or shrink in size. If you're unsure whether to use an array or a vector, chances are you should use a vector. Chapter 8 discusses vectors in more detail. However, arrays are more useful when you know the number of elements will not need to change. For example, if you're using the numbers of the months in a program, you would probably use an array rather than a vector because you know it will always contain 12 elements. And we are not going to type that out. I mean, we could copy that one, I suppose. Whoops. Oh, that copied all of it. Okay, we're just Control Z that. I just don't feel like typing all those out, but we can kind of get the gist of what they're doing there. And of course, it's not going to change because we don't add like the month of Tyler at all, right? They stay standard months. You write an array's type using square brackets with the type of each element, a semicolon, and then the number of elements in an array, like so. Okay. Let's try that. So let A, we're defining the type of I32 and 5. Okay, what's the 5? You're in array's type in square brackets with the type of each element, a semicolon, and the number. Oh, and that's just saying here's the number of elements that are in our array over here. 1, 2, 3, 4, 5, like that, and like that. Here, I32 is the type of each element. After the semicolon, the number 5 indicates the array contains 5 elements. You can also initialize an array to contain the same value for each element by specifying the initial value, followed by a semicolon, and then the length of the array in square brackets is shown here. Okay. So let A equal 3, 5. So that means 3 5 times. The array named A will contain 5 elements that will all be set to the value 3 initially. This is the same as writing let A equals 3, 3, 3, 3, but in a more concise way. So if we do like print, what was it? How did they do that? When they pulled it out of the list. Yeah, like, so they're specifying that. So if we did let 3 equal a-0 and then print, well, not 3. Let's, we need to spell that out like that. And then if we print line on that beast and we say the 3 is 3 like that, will that compile? Will that print? Will that pull the 3 from the stuff up there? Nope. Cargo run, compiling error, no field 0 on type integer 5, no field 0. So it's a little bit different than a tuple. The array type is different than the tuple. The tuple, we could just pull it out of there. The array type is going to be a little bit different. It would appear. Let's keep reading. Let's see if we can figure this out. Let's delete the stuff I did. Of course, that makes A 3s. So if we just printed A, I wonder if it would do it then. The array named A will contain 5 elements that will all be set to the value 3 initially. This is the same as writing let A equals 3A3, but in a more concise way. Accessing array elements. Here's what I was trying to do. An array is a single chunk of memory of a known fixed size that can be allocated on the stack. You can access elements of an array using indexing like this. Okay, so let A equal 1, 2, 3, 4, 5. So let's just change this to match the example like that. Okay. Let first equal A. I see. So we're doing it that way. And that should pull down 1. And let second equal A. And that should pull down 2. And then if we do print line like that, we can say the first number is first and the second number is second. Right? Does that look right to you guys? I hope it does. First number is 1 and the second number is 3. Oh, good point. Jenny said you'll get 3 for a second, of course, because once again, remember guys, it counts 0, 1, 2, 3, 4. So when we do 2, it's actually 0, 1, 2. We're going to be hitting the 3 there. They did 1, I did 2, but good call. Good learning. In this example, the variable name first will get the value 1 because that is a value at index 0 in the array. The variable name second will get the value 2 from the index 1, or it'll get the value 3 because you're not paying attention in the array. Invalid array element access. Let's see what happens if you try to access an element of an array that is past the end of the array. Okay, so say you run this code similar to the guessing game in chapter 2 to get an array index from the user. All right, guys. I know you might get annoyed at me at this point, but once again, I want to type this out to continue to build that muscle memory. So let's type out this entire code and kind of explain it as we go to see if we're learning some of the stuff. So the first thing we're doing is we're setting an array, which is what we've been working on. So an array with 1, 2, 3, 4, 5, like that. And then we're printing a line to the user, apparently. Please enter an array index, like that. And then we're setting a variable called index, which is mutable, hence the MUT. Index equals, and it's a string. We want a new string that's going to be put in that index variable. And then IO means input output. So this is how we're getting the value from the actual user. 1, 2, 3, 4 to do our spaces properly. Read line. Let's see, the ampersand. Mute index, that's just we're specifying that the index variable that we're doing is mutable once again. And dot expect, if it's not actually a array that we're being given, it'll say failed to read line. So we're kind of catching the error there. And now we're doing let index usize equals index. What's usize again? Maybe they'll explain it. I remember them talking about it in all their number stuff. let uSize equal index. And I notice we don't have a semicolon on the end here because it's all part of one kind of statement. Trim, parse, expect, index entered was not a number, like that. And then let element equal a index. So then we're setting our element from a. Where's the a coming from? Let element equals a index. Oh, up here, of course. A is defined up here. So that's where it's pulling the index down. Let element equal a index. Okay, I got it. Let's add that onto the end. And then finally we'll print line the value of the element at index is element, like that. Okay, what are the chances I made an error while I was typing? I'm sure there's very good chances I made an error while we're typing. Let's find out. Yep, okay. Let's see what error we made here. Use of undeclared crate or module. Okay, I know that error. We forgot to declare it at the top, and we also would have to declare it in our TOML file unless it does it automatically. I'm not sure. But let's see what other errors we have. This is help, add that in there. Okay, I just forgot to add that. Please enter an array index, unexpected token. Don't know what that means. Failed to resolve. Use of undeclared crate or module. We need to declare that at the top. Okay, let's see if we can work our way through the errors that we have. The first thing we need to remember to do is declare, kind of like in Python when you have a new library, we're declaring the standard library, IO like that. And I forgot to add this here. I didn't understand the other error, so let's see what happens now. Hey. Look at that. It worked. We compiled it. We read the errors. Now, what if we do 10? Thread main panicked. Index is out of bounds. The length is 5, but the index is 10. What are we going to do? No, run with Rust backspace equals 1 environment variable to display a backtrace. What do you guys think that'll do? Let's go ahead and copy that. Oh, I'm in a terminal. I need a Control-Shift-C. So run with Rust backspace 0. What did it call it? Environmental variable. I don't know how to declare that. There, I declared it. Let's see what that does. Okay, expected one of exclamation mark or that. Okay, well, we can give you that. Let's do this. What's that do? Okay, let's just let them tell us how to do that part of it. I'm sure that's what they're going to talk about next. I'm working my way ahead. All right. Oh, you need to do that in the shell before cargo run. Oh, obviously, if it's an environmental variable. So let's try that. Good call. So if we do Rust backtrace equals 1, like that, and then if we do cargo run, and then if we do 10, Rust, I'm probably just doing it wrong. I don't know how to do it in Rust. Oh well. They'll explain it to us. It's all good. Okay, this code compiles successfully, unless you're like me. If you run this code using cargo run and enter 0, 1, 2, 3, or 4, the program will print out the corresponding value of that index in the array. If you instead enter a number past the end of the array, such as 10, we actually selected the exact number they're using an example. You'll see an output like this. Thread main panicked. Rust backtrace 1 environmental variable. The program resulted in a runtime error at the point of using an invalid value in the indexing operation. The program exited with an error message and didn't execute the final print line statement. When you attempt to access an element using indexing, Rust will check that the index you've specified is less than the array length. If the index is greater than or equal to the length, Rust will panic. The check has to happen at runtime, especially in this case because the compiler can't possibly know what value a user will enter when they run the code later. This is an example of Rust's memory safety principles in action. In many low-level languages, this kind of check is not done, and when you provide an incorrect index, invalid memory can be accessed. that would essentially be a buffer overflow, right? If I'm remembering my OSCP stuff properly, that's essentially what a buffer overflow is. We're overflowing the buffer, we're accessing invalid memory. And then eventually, once we specify as we're doing the buffer overflow, that's how we can eventually get code execution. Don't quote me on that, because I may be just making that up as I talk. Rust protects you against this kind of error by immediately exiting instead of allowing the memory access and continuing. Chapter 9 discusses more of Rust error handling and how you can write readable, safe code that neither panics nor allows invalid memory access. Well, guys, I wanted to make it through all of Chapter 3, but I also wanted to keep myself kind of at an hour here. And we have another section of Chapter 3 to go through: functions, comments, and control flow. So I think what I'm going to do now is let's go ahead and just pause our learning for now. We made it through an hour of learning Rust. And when it comes to programming, in my opinion, it's important to take it in small chunks to absorb what you're doing and then to review the code later. And so my plan is to stream again. I don't know if I'll do Rust every time. I think I'll probably do Rust again tomorrow night. And maybe tomorrow we'll finish working our way through Chapter 3 and we'll review what we learned up until that point. And hopefully these pieces will start coming together for me and start coming together for you as well. So for those of you hanging out with me on Twitch, thank you. Appreciate you guys joining me live and learning with me. For those of you watching after the fact on YouTube, I also appreciate you guys being here. Hopefully you learned something with me. I know I did. And I hope you guys have an awesome night. And I will catch you guys in the next video. See ya.